Hello there. Welcome to another video from Neurology. So from this time, I've decided to have lots of changes in my channel. So basically, previously I was like making content first by reading some of the article, trying to understand them myself and then explain them. But now we want to do something different. It would be like more like a live stream. So I may have more mistakes. Obviously, I had, but would be more. But it would give me the opportunity to have more video, to be more active. And also, sometimes, like, we can read some articles together, and maybe the video get a little longer. And I will try to have a small edit on top of that, but it will not go to the like the heavy editing or removing many part of it. So bear with me and support. Thank you. For this video, I have chosen this article. I usually like the posts from Lillian, Lil Log, and I think she is working in OpenAI, and she had lots of great content. I always follow the post here. So what I have chosen here is the latest one. It's published in June 2023. And let's see what it is. LLM powered autonomous agents. Let's read through it. I haven't read it. Building agents with LLM, large language model, as its core controller is a cool concept. Several proof of concept demos, such as AutoGPT, GPT Engineer, and Baby AGI, serve as inspiring examples. The potential of LLM extends beyond generating well written copies, stories, essays, and programs. It can be framed as a powerful general problem solver. Yeah, I agree with the all of this, but I haven't heard about Baby AGI. It was interesting for me. So it's a this is a Python script is an example of AI-powered task management system. The system uses OpenAI and vector databases such as Chroma. So there are lots of applications coming just by like uh, following the disaster LangChain repositories. And yeah, there are lots of application from like PDF search, database search, or stuff like that, or summarizing content. So here I think it's doing that, but with some help of agent. I don't want to go through that. So agent system overview. In LLM power autonomous agent system, LLM function as the agent brain, complemented by several key components. Planning, memory, tool use. So yeah, subgoal and decomposition is the first part of the planning. The agents break down larger tasks into a smaller, manageable sub-goal, enabling efficient handling of complex tasks. Reflection and refinement. The agent can do self-criticism and self-reflection over past actions, learn from mistake and refine them for future steps, thereby improving the quality of final result. So this is like the part related to reinforcement learning. Yeah. And then we have memory, short-term memory. I would consider all the in-context learning, for example, prompt engineering, as utilizing short-term memory of the model to learn. And long-term memory to provide the agent with the capability to retain and recall infinite information over extended period, often by leveraging an external vector store and fast retrieval. Yeah, this is the part like ChromaDB or VectorDB coming. And so we have some prompt, and then we have also some long-term memory, some long-term information that we can use them. So let's go back. So we need to split the task to smaller parts, have reinforcement learning, have vector DB, have a prompt, have a good prompt, and then tool use. The agent learn to call external API for extra information that is missing from the model weight, including current information, code execution capability, access to the proprietary information sources, and more. Yeah, yeah, that is the whole definition of the LLM powered autonomous agent. Yeah. So component one is the planning. So it's going to each of these part. First of all is the task decomposition. So how we want to do the task decomposition? First of all is the chain of thought. You already know about it. Yeah, if you haven't heard about that, watch one of the videos I've previously recorded. Another was Tree of Thought. Tree of Thought is uh, published recently. I haven't created a video on top of that, but this is very similar. It's extend chain of thought by exploring multiple reasoning possibility at each step. At first, they compress the problem into multiple thought steps and generate multiple thought per step, creating a tree structure. The search process can be the BFS, breadth first search, or DFS, depth first search, with each state evaluated by a classifier or majority vote. So there is another cool article by Lillian, um, Prompt Engineering. I recommend you to read this. It's talking about like ensembling, like chain of thought, how that works, like how we can get the like tree of thought, the good explanation there, how people can use like the voting there or stuff like that. So task decomposition can be done by LLM with a simple prompting. A step for XYZ, what are the sub goals for achieving XYZ by using task specific instruction? For example, write a story outline for writing a novel or with human inputs. Another quite distinct approach, LLM plus P, involves relying on an external classical planner to do long horizon planning. This approach utilizes the planning domain definition language PDDL as an intermediate interface to describe the planning problem. In this process, LLM translates the problem into the problem PDDL, then second, request a classical planner to generate PDDL plan based on an existing domain PDDL, and finally, translate the PDDL plan back into natural language. Yeah, this is a little complicated. Essentially, the planning step is outsourced to an external tool, assuming the availability of domain-specific PDDL and a suitable planner, which is common in the certain robotic setup. Oh yeah, so I got this. I don't know which is this paper, Empowering Large Language Model with Optimal Planning Proficiency. So I can say this is very similar to something like Viper GPT. I have another video about Viper GPT if you look at that. So we are using language model to do the task decomposition by converting the output of the language model to a smaller command runnable by Python or any other language. So the next part is a self-reflection. Self-reflection is a vital aspect that allows autonomous agent to improve iteratively by refining past action decisions and correcting previous mistakes. It plays a crucial role in the real-world task where trial and error are inevitable. React. This is one of the paper. So one of the cool thing about the Lillian uh, post is that when you read that, you will be familiarized with lots of recent papers. So React integrate reasoning and acting within LLM by extending the action space to be a combination of task-specific discrete action and a language space. Oh, okay, that was really long. The former enables LLM to interact with the environment, like Wikipedia search API, while the later prompting LLM to generate reasoning traces in natural language. Yeah. Let's see some example. The React prompt template incorporates explicit steps for LLM to think, roughly formatted as this is thought, action, observation, repeated many times. Yeah, I remember one of the paper I was talking about. I don't remember the name of that, but it was doing so, like getting some of the information. I think it was Toolformer, I think. So it was like getting a reflection, then going to that tool, get some API back, create a new prompt, continue on top of that. Yeah, it's very similar to this. In both experiment, a knowledge-intensive task and decision-making task React work better than the act-only baseline where thought step is removed. So let's see. Set thought one. I need to search Apple Remote and find the program it was originally designed to interact with. So act one is search Apple Remote. So it first take what is act, and it will search that, and it will return some observation like the Google search. The Apple Remote is a remote control introduced in blah blah blah. Okay, so then we have this, maybe another prompting, and it will detect that Apple Remote was originally designed to control the control the front row media center program. I need to search front row next and find the other device can control it and do the second act. Yeah, this is really interesting. Yeah, this is very similar to Toolformer, if I'm not mistaken. And it's like getting some information, creating new prompt, continue to this path until we reach to the point that this is done, this is finished. Another one is reflection. Reflection is a framework to equip agent with dynamic memory and self-reflection capability to improve reasoning skills. Reflection has a standard reinforcement learning setup. As I said, the reflection part may have reinforcement learning. In the previous one doesn't. It's like using just LLM itself, but this time it has reflections. In which the reward model provides a simple binary reward and the action space follows the setup in the React, where the task-specific action space is augmented with language to enable complex reasoning steps. This is really cool. So it means like we have this, but how how we are gonna like take the next action is decided by a reinforcement learning and the long-term memory. So after each action, the agent compute the heuristic and optionally may decide to reset the environment to start a neutral depending on the self-reflection result. And this is really cool. It's comparing the success without reflection, success with reflection. That success rate is increased a lot. Oh yeah, there are some cases that there are like hallucination. So we were here. The heuristic function determines when the trajectory is inefficient or certain hallucination and should be stopped. Inefficient planning refers to the trajectory that takes too long without success. Yeah, so how we are gonna be sure that this is not going to infinity? So there are like some reinforcement learning in there help us to predict the value, I think, or something like that. And if the value is not good, restart it from scratch. It's like the tree, the chain of thought and the tree of thought is very simple to this, similar to this, but this time instead of tree, we have reinforcement learning. Hallucination is defined as encountering a sequence of consecutive identical action that lead to the same observation in the environment. Self-reflection is created by showing two-shot example to LLM, and each example is a pair of failed trajectory, ideal reflection for guiding future changes in the plan. Then reflections are added into the agent working memory up to the tree to be used as a context of querying LLM. Chain of insight. COH encouraged the model to improve on its own outputs explicitly, presenting it with a sequence of past output, each annotated with feedback. Human feedback data is collection of these, where X is the prompt, Y is a model compilation, R is the human rating, Y and Z is the corresponding human provided insight feedback. Assume the feedback tuple are ranked by reward Rn 2 or 1. The process is supervised fine-tuning where the data is a sequence in the form of this. So I'm not going continuing on that, but this is like a continuous approach of reinforcement learning with human feedback. Yeah. So instead of like getting the action and values from reinforcement learning, now we have human in the loop. So the idea of COH is to present a history of sequentially improved outputs in the context and train the model to take on the trend to produce better outputs. Algorithm distillation applies the same idea to cross-episode trajectory in reinforcement learning tasks, where an algorithm is encapsulated in a long history condition policy. Okay, I haven't heard about this paper too, algorithm distillation. But it said algorithm distillation applies the same idea to cross-episode trajectories in reinforcement learning tasks. where an algorithm is encapsulated in a long history condition policy. Considering that an agent interacts with an environment many times, and each episode the agent get a little better, AD concatenate this learning history and feed that into the model. Okay. Hence, we should expect the next predicted action to lead a better performance than previous trial. The goal is to learn the process of RL instead of training task-specific policy itself. It's really interesting for me that what exactly is happening here in context reinforcement learning with algorithm distillation. I really like to read this paper, how this works. I'm going to save it on my AI should read. You see, I have lots of things to read, but I think this is worth to have it. Algorithm distillation. Maybe we will have another video on top of that, but this is really cool. It's like during training reinforcement learning, we have some sort of meta learning to learn the algorithm better. This is really cool. The paper hypothesized that any algorithm that generates a set of learning histories can be distilled into a neural network by performing behavioral cloning over actions. The history data is generated by a set of sources policies, each trained for a specific task. Oh, this is really cool. Yeah, it's going to much deeper details that maybe it's not necessary for now, but it's cool. At the training stage, during each reinforcement learning run, a random task is sampled and a subsequence of multi-episode history is used for training, such that the learned policy is task agnostic. In reality, the model has limited context window length, so episodes should be short enough to construct multi-episode history. Multi-episodic context of 2 by 4 episodes are necessary to learn a near optimal in context RL algorithm. Yeah. So and there's some comparison like between the algorithm distillation and ED. What was ED? It was expert distillation. Yeah, my knowledge in the reinforcement learning is old, back to 2-3 years ago. There are lots of improvement in this. I think this is like very similar to the distillation that we've done between teacher and student in machine learning. Now we have like an expert, and we are like distilling that. So that expert distillation, remember, it can happen like by help of a real expert by annotated data with some data, or with another trained model. I think I have some video on about that, but it's like too much times pass. Yeah. So the second component is memory. Big thank you to ChatGPT for helping me draft this section. I've learned a lot about the human brain and data structure fast MIPS in my conversation with ChatGPT. Cool. So Lillian is also working with ChatGPT for writing some of this. Cool. Types of memory. Memory can be defined as the process used to acquire, store, retain, and later retrieve information. There are several types of memory in human brain. Sensory memory, short-term memory, long-term memory. Short-term memory, like storing information for a short time, and it's believed to have the capacity of about 7 items and lasts for 20-30 seconds. Cool. Long-term memory can be stored information for a remarkably long time, ranging from a few days to decades. With an essentially unlimited storage capacity, there are 2 types of long-term memory: explicit memory, implicit memory. Explicit memory, this is memory of fact and events, and refer to those memories that can be consciously recalled, including episodic memory and semantic memory. Event and experiences are in a different portion than like the memory that we learn and a skill. Implicit memory is like involving skills and unconscious, like riding a bike or car. But remembering something with semantic memory of fact or concept is different thing. Sensory memory is like just lasts for a few seconds, and after the stimuli have ended, for example, like watching something, if I close my eye, sensory memory is done. Sensory memory has learning embedding representation for raw inputs, including text. Yeah, when I touch this, I'm feeling this in a way because this is coming from my sensors, sensory memories. So when I converting some information to embedding representation, it's like sensory memory. And then short-term memory, so it's short and finite as it's restricted by finite context window of the transformer. So we have short-term memory as in context learning. Long-term memory as external vector store that agent can attend to a query time at a query time accessible by a fast retrieval. So we have all of this part. So maximum inner product search, MIPS, what it is. The external memory can alleviate the restriction of finite attention span. A standard practice is to save the embedding representation of information into a vector store database that can support fast maximum inner product search. To optimize the retrieval speed, the common choice is the approximate nearest neighbor algorithm to return approximately top k nearest neighbor to trade off a little accuracy loss for huge speed up. Oh yeah, I was reading a paper this weekend. I think I can show it to you. It's in my Dropbox still. I wasn't able to finish it because it was really hard to do it. Billion similarity search. It is exactly what it is talking about. So these people, I think from NVIDIA, if I'm not wrong, from Facebook, sorry, uh, they, I think they are explaining the way that Face library, FAISS library for search is implemented now for GPU, optimized GPU search on a million records, on a million vectors. And this is really hard to grasp because I didn't have any clue how GPU work, but it was really well written. Give you lots of information if you like reading it and search it while you're reading it. So I think this is some sort of this like talking about different way, like face, as I said, the way that they are doing that. Um, there are other methods like scan, scalable nearest neighbor, stuff like that. Let's see, like it's showing here a speed per second for a scan is really amazing. Where is face? Okay, yeah, I was reading that paper and I said, oh, that's really state of the art, should be, but you see that paper 2017 now 2023, how much improvement we have. So scan, the main innovation of scan is anisotropic vector quantization. It quantizes a data point x to x hat such that the inner product is similar to the original distance as possible instead of picking the closest quantization centroid points. Interesting. So it means like quantize a data point to something that doesn't need multiplication because in the paper here it was mentioning that the main challenge for like vector search, there was an equation here like this one, is this, which is a matrix multiplication, and the main part calculating this is not difficult. The main part is calculating this inner product, and this way scan is saying that we are quantizing this value somehow that you don't need to multiply. This is interesting. And that is opening another area for me to search. So, and the last component is tool use. So this component, the type of memory that we have, we explained it sensory, short term and long term. For long term, we need something that we can search very fast, and we have some method that we can search very fast. And of course, you can see that the accuracy and the speed, comparing these together. And the first component already we have it, like the way that we want to get the information, the reflection, yeah, the planning. Now we have planning, we know what we want to do. We have some memory. Now we need the tool that we want to use, like some external API. Yeah, so it said tool use is remarkable and distinguishing characteristic of human being. We create, modify, and utilize external objects to do things that go beyond our physical and cognitive limits. Equipping LLMs with external tools can significantly extend the model capabilities. MRKL, short for Modular Reasoning Knowledge and Language, is a neurosymbolic architecture for autonomous agents. A MRKL system is proposed to contain a collection of expert and general purpose LLM work as a router to route inquiries to the best suitable expert module. This module can be neural or symbolic, math calculator, currency converter, weather API, stuff like that. Yeah, and here they're just like calling different tools. Like first one is this one, the second one is TALM, Tool Augmented Language Model, or Tool Former. I think this was the paper I explained. And yeah, ChatGPT plugin is another tool, or even Hugging GPT is another tool. And task planning, model selection, task execution. Okay, this is really cool. And response duration. There is another paper is introducing here API Bank is a benchmark for evaluating the performance of tool augmented LLMs. Contain 53 commonly used API tool, a complete tool augmented LLM workflow, and 264 annotated dialogue that involve blah 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 API calls. The selection of API is quite diverse, including search engine, calculator, calendar query. So it means that like we are giving a computer to a LLM, and we are also enabling agent with reinforcement learning, so during time it can learn. Yeah, so it is like a path toward AGI, I feel. Because there are a large number of API, LLM first has access to API search engine to find the right API to call and then uses the corresponding documentation to make a call. And suppose that all of these would be like in a second, that would be amazing. Yeah, so there are some case studies here, scientific discovery agent. Let's say this. ChemCrow is a domain-specific example in which LLM is augmented with 13 expert design tool to accomplish tasks across organic, synthetic, drug discovery, and material design. The workflow implemented in LangChain reflects what was previously described in React and MRKLS and combine chain of thought reasoning with tools relevant to the task. This is really interesting. Of course, don't use LangChain. Why people use LangChain at all? Because it's just like a wrapper around LLM. You can write everything that you want. Maybe you have better control over it. And LangChain is buggy. It's really buggy. And it's actually nothing. It's not like bringing new technology to the system. So it's really interesting that like in the domain like drug discovery, maybe they have different part like organic, synthetic, drug discovery, material design, stuff like that. And people can just interact with the agents and the agent know what to do with those data. Yeah, it said LLM is provided with a list of tool names, description of their utility, and details about expected input-output, then instructed to answer user-given prompts using the tool provided when necessary. And it's using React, so we have thought, action, action input, and observation. And it's saying here, interestingly, that ChemCrow outperformed GPT-4 by large margin because this is like specifically designed for this purpose. Yeah, this indicates potential problem with using LLM to evaluate its own performance on domains that require deep expertise. The lack of expertise may cause LLM not knowing its flaws and thus cannot well judge the correctness of task result. Yeah, this is really true. Even if you look at like some of the result coming from zero-shot prompting of language model on a specific task, you cannot compare it with another simpler model specifically trained for that task. So when something need to be trained on a like a specific task, like deep expertise, it should be trained on that. So they also discover risk, especially with illicit drugs, bioweapons. They develop a test set containing a list of known chemical weapon agent. What? And ask the agent to synthesize them. Interestingly, 4 out of 11 requests, 36% were accepted to obtain a synthetic solution, and the agent attempt to consult documentation to execute procedure. and 7 of 11 rejected. And among these 7 rejected, 5 happened after a web search, while 2 were rejected based on prompt only. Oh yeah, so this is something that people should think about it. So uh, we will create like a powerful tool, but we should have some sort of, I don't know, some sort of control over it. Maybe another machine learning over the LLM just to detect that this is not appropriate. I don't know. Um, or just fine tuning that LLM to not respond to those questions. Sometimes I think because this is like a black box, like making it secure is much harder. So generative agent simulation. This is also interesting. It's at Park and it all did a generative agent, a super fun experiment where 25 virtual characters, each controlled by LLM power agent, are living and interacting in a sandbox environment inspired by The Sims. And generative agent create believable simulacra of human behavior for interactive. I don't know what this word. I haven't heard that. Hmm, okay. Of human behavior for interactive applications. The design of generative agent combine LLM with memory, planning, and reflection mechanism to enable agent to behave condition on past experience as well as to interact with other agent. Yeah, cool. So it's like other part that we've described, like reflection. So it's that memory history. It's a long-term memory that record a comprehensive list of agent experience in natural language. Each element is an observation and event directly provided by agent. Inter-agent communication can trigger new natural language statement. Retrieval. Surface the context to inform the agent behavior according to relevance, recency, and importance. Recent events have higher scores. Importance, distinguish mundane from core memories. Ask LM directly. Okay. So I'm not going to the details of this, but it's like showing like during a time we have some sort of evolution. The fun simulation result in emergent social behaviors such as information diffusion, relationship memory, to agent continuing the conversation topic, and coordination of social event, like host a party and invite many others. Oh, this is really cool. Uh, Let me check that too. Generative agent interactive simulacra. Let's see. Yeah, it is in Sims, course 2D, and common room, family house. That is really cool. Yeah, it is done by Stanford. Yeah, it's really cool. The way that like these simulation need to be written is really interesting because um, I think like it needs lots of machine there. I think this is really hard because each agent there, each person out there can learn. So we have a really great, I don't know what is the size of each LLM there, but it is LLM, it should be large. But they are already training, I think. So there's a massive graph there for each agent that during each interaction, it's getting trained. Of course, this is just one part, but it's really hard. I don't know. Maybe I should read that paper to get some idea of how people are doing that. But for me, it's like training this is really hard. Just based on languages, it would be really hard. Yeah. At the end, these are the challenges. I think this is the conclusion of the article. After going through key ideas and demos, I start to see a couple common limitations. Finite context length. The restricted context capability limits the inclusion of historical information, detailed instruction, API call context, and responses. The design of the system has to work with the limited communication bandwidth, while mechanisms like self-reflection to learn from past mistakes would benefit a lot from long or infinite context window. Yeah, exactly. Also, vector store and retrieval can provide access to a large language pool. Their representation power is not a powerful full attention. Let me read it again. Also, vector stores and retrieval can provide access to a larger knowledge pool. Their representation power is not as powerful as full attention. Yeah. So that's the main thing, a finite context length. So at the end, of course, we are using like long-term memory, but we are not using that information as when we're using attention layer. And also, another important thing is that if you use, for example, React or other reinforcement learning can get better. I think that's one of the reasons that we have long-term memory in the reinforcement learning. Yeah, I'm not sure that these long-term memory here being using the reinforcement learning uh, like actor critique method that we have a memory there. I don't know about that. My knowledge about reinforcement learning is old, but uh, this is a valid context. And as I said about that social behavior paper, um, it's really hard to train these models because we don't have the whole information there. And training would be huge if we have all of them. So that's some sort of like covering my point that, of course, we haven't used those information. That's why it's a little easier to train those. Challenges in long-term planning and task decomposition. Planning over a lengthy history and effective exploring the solution space remain challenging. LLMs struggle to adjust plans when faced with unexpected errors, making them less robust compared to human when learned from trial and error. Yeah. So we have two parts, extrapolation and interpolation. For extrapolation, we should use some symbolic learning, like using swarm optimization or something maybe. And I think we already doing that in our mind. Another one is reliability of natural language interfaces. Current agent system relies on natural language as an interface between LLM and external components such as memory and tools. However, the reliability of model output is questionable, as LLM may make formatting error, occasionally exhibit rebellious behavior, refuse to follow instruction. Consequently, much of the agent demo code focuses on parsing model output. Yeah. So uh, one of the cool part, one of the research I found was related to DeepMind was fixing sorting algorithm on assembly. If you have read that, it's like using LLM or not, sorry, not LLM, using the AlphaFold, the algorithm in the right space, in the right domain. Actually, it was like a symbolic search, like it's like a symbolic learning. But for LLM, it is language model, so we cannot expect to have like non-language there. Yeah. Uh, so at the end, it's something that need to be parsed, compiled to something. What if? So that's one of the reasons like we have Copilot, and I think Copilot is being used, I think, more than ChatGPT because the outcome of that can be used directly in the product in the external interface that we want to use. But for language model, if we want to extract something, we have to parse it. Even for entity extraction, even for some question answering, we have to parse it, extract those information. That's why there are lots of like prompt engineering there to like just predict the blank, like asking in a prompt, just predict the blank part to reduce the parsing part, you know. So at the end, it would be, it's also, sorry, it also um, justify the point I mentioned that those agents are just contacting with each other with language, and how we want to interpret those language, and we use those language, use those things for reinforcement learning again, for retraining. Because language is vast, and yeah, you got the point. Yeah, thank you. It was a great read. I hope you enjoyed the video. Have fun. We will have lots of fun together soon.